Okay, let's restart maybe. So today's class will be about ligand field theory of tetrahedral complexes. And when we have tetrahedral complexes, then we are in the point group TD. And we first have to think about the metal frontier orbitals of our complex. So I've told you in the last class, or maybe the class before, that one can inscribe a tetrahedron into a cube, which is shown here. Okay, and that tells you basically how to choose the axes. So we can have the axes pointing through the faces of our cube. So the x-axis, for instance, can point to the right, standing perpendicular to this face here. The y-axis can point to the front, standing perpendicular to this face, and this axis here, the z-axis, stands perpendicular to this face over there. So that will define the orientation of our orbital. So let's look at the valence orbitals of our metal in more detail. So if we choose again have fourth period transition metal, then the orbitals to consider would be the 4s, the 4p, then the 3d orbitals, the 3d xy, the 3d yz, the 3d in the 3d xz, as well as the x square minus y square in the dz square. So what symmetries will these orbitals have? We can determine this directly by looking into the character table. So the s orbital always has totally symmetric representation. That's always the first one in the character table. So that's in this case A1. Okay. So the 4p orbitals we find here. So x, y, and z are in parentheses, so that means that they're again triply degenerate, and the exact symmetry type is T2. So the 3dxy, the 3dyz, and the 3dxz, we find actually here. So they're also triply degenerate, and they also have the symmetry type T2. And last but not least, there are the 3dx square minus y square and 3dz square. And you find them actually here. So the 3dz square, again, you find in the form 2z square minus x square minus y square, because the wrong form of the 3dz square orbital, if you will, which describes the cone. And after that, we see here the x square minus y square listed. So these orbitals have the symmetry type E. Okay, so next we have to look at our ligands and our ligand orbitals. Again, the ligand orbitals depend on what ligand we have. So we have to construct the molecular orbital diagram of our ligand and select then the highest occupied molecular orbital that is suitable for sigma bonding. So again, we could choose, for instance, a carbonyl ligand, and we have seen what the highest occupied molecular orbital of the carbonyl ligand is in the last class. Okay, now in this case, however, the situation is a little bit more tricky because of the coordinate system. So we have assigned the coordinate system in order to, in the way we just discussed it, in order to basically determine what's the orientation of our metal d orbitals. But now what about our ligand orbitals? So if we say the bond axis of our CO ligand defines the z direction, then our CO ligands would all be pointing vertically if you chose the same coordinate system. And then the orientation of the respective orbitals would be according to that. Okay, And that would mean that here, this electron lone pair here at the oxygen would point upwards, and the electron lone pair here at the carbon would point downward. Yeah. So now this is not suitable in order to maximize bonding. Okay, we want to create a sigma bond in which the orbital overlap is being maximized. Therefore, this orientation of our ligands isn't suitable. Okay, so for that reason, we have to give each ligand its own coordinate system so that the ligands can point to the center of our tetrahedron in order to maximize the bonding. And that means that each ligand now will get its own coordinate system. Okay? So, for instance, this ligand here has, again, the z-axis now along the direction of the carbon-oxygen bond, and the x and the y-axis would stand perpendicular to that. This CO ligand would have its z-axis pointing toward this CO bond, and the x and the y-axis would stand perpendicular to that. So basically, we choose our coordinate system so that we are maximizing the orbital overlap with regards to sigma bond. Okay, now what do we need to do in the next step? Well, again, we have to determine the irreducible representations of our ligand group orbitals. Okay, so in this case, we have 4 homos to consider, okay, because we have 4 CO ligands. So therefore, we overall have to combine 4 homo orbitals to form ligand group orbitals. So again, we would need to determine the reducible representation and then irreducible representation, which would give us the symmetry types. Okay, so now I again do not go through the exact mathematical formalism again, but just present you the results. So the result would be that one ligand group orbital has the symmetry type A1, and there are 3 other ligand group orbitals that have the symmetry type P2. So these 3 ligand group orbitals are triply degenerate. Okay? So now, with this knowledge in hand, we can now construct our molecular orbital diagram for sigma bonding. So what we again first can do is plot the matter frontier orbitals on the left side and assign the symmetry types accordingly. So the 3D, the 4s, and the 4p. So the 3D will have E and T2 symmetry, the 4s has A1 symmetry, and the 4p has also T2 symmetry. So then we have our 4 ligand group orbitals. One has A1 symmetry and one has T2 symmetry. We plot them with similar energy on the right side of the molecular orbital diagram. So now again, we can just combine orbitals of the same symmetry type to form molecular orbitals. Which symmetry type we start is again arbitrary. We can, for instance, start with a symmetry type A1. So we realize that the 4s orbital has the symmetry type A1, and also one of the 4 ligand group orbitals has the symmetry type A1. That means that we will get 2 molecular orbitals of the symmetry type A1, and one will be bonding, having lower energy, and the other one will be interbonding, having higher energy, and we can label them 1A1 and 2A1 respectively. So then we can go to the next symmetry type. We can, for instance, choose the symmetry type P2. So now we realize that 3 of the 3D orbitals have that symmetry type, but also the 4p orbitals have that symmetry type. Now, in addition to that, on the ligand side, 3 ligand group orbitals have that symmetry type. So overall, we combine 9 orbitals, and that means that we need to get 9 molecular orbitals. But it has to be 3 sets of triply degenerate orbitals, okay? And when we have 3 orbitals or 3 sets of orbitals, then we can approximate that one will be bonding, it will have low energy, one will be interbonding, having high energy, and the third one will be approximately non-bonding, can be weakly bonding or weakly interbonding, and has intermediate energy. We can write the orbitals accordingly into the molecular orbital diagram. Okay, so now you see here the 1T2, which has low energy, here the 2T2, which has intermediate energy, and here the 3T2, the interbonding one, having high energy. So now what's left? What's left is these 2 3D orbitals that have E-symmetry. And you see that these orbitals do not find a bonding partner. So they remain non-bonding with regards to sigma bonding. And we have to write them accordingly into our molecular orbital diagram, and we can just label these orbitals E. So now again, we have to fill in the electrons. And again, we consider the bond and dative bond. That means that we say that the ligands donate 2 electrons into the metal orbitals. Okay, through the homos, which are 4. And that means that all of our ligand orbitals have to be filled with electrons. And we have overall 8 electrons that we now need to fill into the molecular orbitals according to energy. So now which orbitals will be filled? Well, that will be the 1T2 that consumes 6 electrons. In addition to that, there will be the 1A1. Okay? So we see that we can easily explain with our molecular orbital theory our 4 bonds in the tetrahedral complex, because we can fill all the ligand electrons in bonding molecular orbitals. All right. So now any metal d electrons would need to go into higher energy orbitals. So we could have up to 10 metal d electrons. I'm adding here 10. So they would need to go into the EG and the 2T orbitals. So we can say again that these are our frontier orbitals in our molecular orbital diagram. So these would be the highest occupied molecular orbitals. Okay. So now again, we see here an analogy in between the crystal field theory and the ligand field theory. So in the crystal field theory, we say that the d electrons split in a tetrahedral crystal field into E and T2 orbitals. Okay, the E orbitals would be energetically lower than the T2 orbital, and the energy difference would be our delta T. So now, here in the ligand field theory, we arrive at a similar result. You see that these E orbitals here are exactly metal d orbitals, but these 2 T2 orbitals can be approximated as metal d orbitals as well, because they have been made from these metal d orbitals, and they are also approximately non-bonding and have energies which are similar than the metal d orbitals from which they have been made. So we can say that these are also metal d orbitals, but they are under the influence of our tetrahedral ligand field now. Okay, so overall we can say that these orbitals here, the E and T2 orbitals, are metal d orbitals that split in energy due to the presence of a tetrahedral ligand ligand field, and that the energy difference between the E and the T2 orbitals would be again a delta T. Okay, now we have to expand our considerations from the sigma bonding to the pi bonding. Okay, so now with regards to the pi bonding, we have to look for molecular orbitals in the ligand that can overlap with metal d orbitals in a pi fashion and still have suitable energy. So in the octahedral case, these were our pi and pi star orbitals of our CO ligand. And when we analyzed the orbital overlap between the pi and pi star orbitals and the metal d orbitals, and we saw that we can create an exact pi orbital overlap, creating a pi bond. So now when you look at the same orbitals in the tetrahedral case, and you see here the bonding pi orbitals of our ligand, then you will see that you cannot create an exact pi orbital overlap with any of the metal d orbitals. Okay, the orientation is not so that you can create a real pi interaction. Okay, but then nonetheless, these pi and pi star orbitals of the ligands, they have suitable orientation so that bonding and interbonding interactions with metal d orbitals do not cancel out exactly. So we can still create a bonding interaction, but it's not exactly a pi bonding interaction, but we can still approximate this interaction as pi interactions. Okay, but we should keep in mind that the relative orientation of these orbitals is not so that we could call it really an ideal pi interaction, but still we can say approximately so. Okay, when you analyze the orientation of these pi orbitals here, for instance, with this metal d orbital, you will see, well, they don't overlap exactly pi, but they still overlap so that we can create a bonding interaction, which we can approximate as pi. So now we can analyze how many pi ligand orbitals do we have to consider to create additional molecular orbitals due to the approximate pi interactions. So in this case, we have only 4 ligands. So 4 ligands, so each ligand has 2 pi orbitals, which are bonding, and 2 pi orbitals, which are anti-bonding. Remember that from the molecular orbit diagram, CO ligand. So in this case, we have 4 times 4, which is equal to 16. So 8 of these orbitals will be pi, and 8 of these, the other orbitals, will be pi star. So we can group the pi orbitals together to form ligand group orbitals, and we can group the pi star orbitals together to form another set of ligand group orbitals. We can again apply the symmetry adapted linear combination of atomic orbital method in order to determine the symmetry types via the reducible representation in the reduction formula that gives you the irreducible representation. If again you applied this formalism, you would find that there are 2 ligand group orbitals that have the symmetry type A, and 3 ligand group orbitals that have the symmetry type T1, and another 3 that have the symmetry type T2. So that gives overall 8. Okay, so 2 plus 3 plus 3 gives 8. Okay, so we have E plus T1 plus T2 for both the pi and the pi star orbitals. So now that we know our symmetry types, we can construct again additional pi molecular orbitals, and we can modify our molecular orbital diagram, taking the pi interactions into account. What you see here on the slide is again the molecular orbital diagram of the tetrahedral complex under the consideration of sigma bonding only. And now we have to take into account pi interactions. So now again, we have to decide whether our ligand is a pi acceptor or whether our ligand is a pi donor. If we choose the carbonyl ligand as the ligand, then we have a ligand which is a pi acceptor, and we should choose our anti-bonding pi star orbitals for creating our additional molecular orbitals. So we should write these pi star molecular orbitals according to energy to the right side of our molecular orbital diagram. So overall, we have 8 orbitals, E, the T2, and the T1. But we only need to consider the E and the T2. That is because the T1 will not find a bonding partner. They remain non-bonding with regard to pi bonding. Okay? That is because here on the left side, for the metal orbitals, we don't see any orbital which has a T1 symmetry. So now having placed our orbitals, we can combine orbitals again in order to form additional molecular orbitals. So we can, for instance, start with the E orbitals, these two here. So they will interact with the E metal D orbitals. Okay? So these are the metal D orbitals which were formerly non-bonding with regard to sigma bonding, and we wrote them accordingly into our molecular orbital diagram. So now, due to the pi interactions, these orbitals now will become bonding, okay? And have lower energy, but of course there also has to be a pair of anti-bonding molecular orbitals also that has a higher energy. Okay? Now again, it's worthwhile to double check the number of orbitals in order to make sure that we have created the right number of molecular orbitals. We started out with 4, okay? So we must have 4 molecular orbitals created. You see, we have here this bonding pair and this anti-bonding pair. All right, so next we can go to the metal to the T2 orbitals. You see that we have here this triplet of T2 orbitals. So that can now interact with the metal 3D orbitals, but it can also interact with the 4p orbitals of T2 symmetry. So now in an approximation, we can consider interactions with the 3D orbitals only because those could be considered having more similar energy, but if we took into account the 4p interactions also, it would not qualitatively actually change a lot. But the fact is that we have here now an additional set of T2 orbitals, so therefore we must create another set of T2 orbitals into our molecular orbital diagram. Okay, so now what needs to happen? Well, these T2 orbitals go down in energy, and we create another anti-bonding set of T2 orbitals. Okay, so now again, the number of molecular orbitals with T2 symmetry is equal to the number of atomic or ligand group orbitals. So you have, you see, 1, 2, 3, 4 sets of T2, and you have 1, 2, 3, and 4. Okay, so that one which was formerly 3T is now the 4T2. Okay, so now what has happened to our delta T? Okay, so now our delta T is defined as the energy difference between the E orbital and the T2 orbital. So now the E orbitals were formerly non-bonding and they are now bonding. And these two T2 orbitals, which were formerly approximately non-bonding, okay, they are now also bonding. But the energy of the E orbitals has been lowered more than the energy of the T2 orbital. Therefore, overall, our delta T has increased, but not much so. Okay? So now you see that the ligand field theory also delivers an explanation as to why in the octahedral case we can find high and low spin complexes, but in the tetrahedral case we never find that. And that is because the delta T cannot significantly increase with the due to the pi interactions, right? That is because both the E and the T2 orbitals get lower in energy. Okay, so now finally we can add our electrons. So we previously had these orbitals here already filled. Now our pi star orbitals here are empty by nature, so no more ligand electrons are being added. But if we had any metal d electrons, we would again need to fill them into the E and the T2 orbitals. So in the case of nickel, and nickel tetracarbonate actually is stable known tetrahedral carbonyl, we would have overall 10 electrons because the nickel is a D10 metal, and in a carbonyl, the nickel is in the oxidation state 0. So we would have to fill the 10 electrons into the 1e and the 2 T2 orbitals. So now we can again analyze if that molecule is expected to be stable. And the answer is yes, because we not only have our ligand electrons in these bonding molecular orbitals down here, but due to the pi interactions, our E orbitals have become bonding, and our 2 T2 orbitals also have become bonding. And all our metal d electrons are in bonding molecular orbitals also. All right. So now we can again also see that our ligand field theory is able to explain the 18 electron rule. Okay, so if we count our electrons, then we would see that our complex is an 18 electron complex. 10 electrons would come from the nickel here, and 8 electrons would come from the ligands. So if we counted our electrons overall, that would give 18. And we find that all these 18 electrons are in bonding molecular orbitals. No anti-bonding molecular orbitals need to be occupied, and that's of course the ideal situation for bonding in a complex. Okay? So here's just again the result that both the T2 and the E orbitals are lowered, E more than T, which results in a net increase of delta T. But again, as I said previously, the increase of delta T isn't much. Therefore, all tetrahedral complexes always stay diamagnetic and stay high spin, and there are never any low spin complexes observed in the tetrahedral case. All right. Now we can also look at an example in which we have pi donor interactions. So for instance, our ligand could be a chloroligand, so halogenide ligand is a typical pi donor, and a metal could, for instance, be titanium. So titanium tetrachloride would be a molecule in which we would have pi donor pi-donor interactions. So how would we need to modify our molecular orbital diagram in this case? So in this case, we would have to add the ligand group orbitals of E and T2 symmetry, which are made from the bonding pi orbitals, not the pi star orbitals. And that, of course, now means that these ligand group orbitals are full with electrons. We would not consider the pi star orbitals because they would be considered energetically too high. So now, again, we could create our additional molecular orbitals now. We could again start with the E-type orbitals. So we have these E ligand group orbitals and the E metal D orbitals. So we would need to create overall 4 molecular orbitals of the symmetry type. So we have already 2 here. So what happens is that these orbitals here would move up in energy, and we would create a pair of bonding molecular orbitals of the type E as well. Okay, so we have a pair of bonding and a pair of interbonding E-type molecular orbitals. So now, what about the T2 orbitals? Well, we would combine these T2 here now with these 3D T2. So now what will happen is that we increase the energy of these T2 and we create another triplet of bonding T2 down here. So what we can do now is we can fill our 10 additional electrons that we had into these 6 T2 orbitals and these 3 T2 orbitals and these 2 E orbitals. So that shows now that we have stabilized our pi electrons in the ligand. Okay, so now what has happened to our delta T in this case? You see that our delta T has declined. The formerly non-bonding E orbitals have become anti-bonding, but our formerly non-bonding 2 T2 orbitals, which are now the 3 T2, have become anti-bonding also. Okay, but again, the effect is greater for E than T2, and for that reason, overall, our delta T has been decreased. And you see again that the effect of a pi donating ligand is an effect of decreasing the delta T in a complex. Okay, but again, the effect is relatively small because both orbitals are being involved. Okay, so now any metal D orbitals, metal D electrons, would need to go either into the E and the T2. In the case of titanium, and the example of titanium tetrachloride, there wouldn't be any because the titanium would be in the oxidation state +4. Titanium is a group 4 metal having 4 electrons in the neutral state. If you remove 4 electrons, then no D electrons are being left. So again, we see that we create the ideal bonding situation with this number of electrons. We see that all our bonding molecular orbitals are being full with electrons, and we see that all our interbonding molecular orbitals are being empty. We can again see if we can explain the 18 electron rule or also the exceptions of it. So now the titanium tetrachloride, considering the sigma bonds only would violate the 18 electron rule, because we would have only 8 electrons coming from the ligand to consider. There would be no D electrons applying the oxidation state method, because the titanium is a titanium 4+. Okay, so this is an example of an early transition metal complex that violates the 18 electron rule. Okay, but we see that we can explain this because when we have only 8 electrons, then all of our bonding molecular orbitals are being full, and we do not need to fill any other orbitals. However, if we took the pi interaction into account, in a sense, the 18 electron rule would still be fulfilled, because then we would add these 10 electrons in the bonding pi orbitals to the valence electrons that are involved in the bonding. And when we add these 10 to the existing 8 that make the sigma bonds, we would even have 18. Okay? But that's what we are not accounting for in our standard of electron counting procedure. So we do not see these additional pi interactions in the way we are counting the electrons. Yeah? But with this ligand field theory, we can actually see that there are more electrons involved in the bonding, in the pi bonding in this case. All right, then we are finished with the tetrahedral case, and we can maybe start with the last case, because we still have a bit of time, and that is the square planar case. So we'll see that a square planar complex gives the most complex molecular orbital diagram of them all, mainly because our symmetry is relatively low. We are now in the point of D4H. And because we're having a relatively low symmetry, we have relatively few orbital degeneracies. Energy degeneracies, and that produces more molecular orbitals with more different energy levels. That creates overall a more complex molecular orbital diagram. But you will see that you can understand this molecular orbital diagram relatively easily if you just apply the symmetry adapted linear combination method correctly, step by step. Okay, so let's approach this case systematically. We only said our point group is D4H. So this is the character table here for D4H. We now need to find our metal frontier orbitals in this character table. So again, if we look at a square planar complex of the 4th period transition metal, then that would be the 4s, the 4p, and the 3d orbitals. So now the 4s would have A1G symmetry, because that's a totally symmetric type. Okay. So then where are the 4p orbitals? Well, you see that the x and the y orbitals are here. The x and the y orbitals, the px and the py orbital, they are doubly degenerate and have the symmetry type EU. And the pz orbital can be found here and has the symmetry type A to U. 4pz has A to U, and the 4px and the 4py have EU. All right, so now what about the d orbitals? So we can look first at the 3dxy, for example. You see xy here in the character table. You see the associated symmetry type is B2G. So next we can look at the 3dxz and the 3dyz. So we find these orbitals here. You see that these orbitals are doubly degenerate, and they have the point group EG. And last but not least, the 3d square orbital can be found here. So z square is here. So we have again symmetry type A1G. Okay, then, sorry, we have forgotten one. That's the 3d x square minus y square. So you see, it's actually here. So it has the symmetry type B1G. You see fairly many different symmetry types because of the relatively low energy. Okay, so now let's go to the ligands. Now again, the orbitals would depend on the ligand. In the case of a square planar complex, we do not know any square planar complexes with carbonyl ligands, but we know square planar complexes with a related ligand, the cyanoligand. And the cyanoligand is isoelectronic with the CO ligand and has essentially the same molecular orbitals, just that their energy levels are slightly different because the nitrogen has a somewhat lower electronegativity than the oxygen. So therefore, the nitrogen orbitals are energetically a little bit higher than the orbitals of the oxygen. But otherwise, there is no significant difference between the orbitals of the CO and the Cn minus. So therefore, also the HOMO of the cyanoligand is the same as for the CO ligand. Therefore, we can just again choose the respective molecular orbital and create our sigma bonds. Okay, now you see here actually the molecular orbital diagram, and here's the respective HOMO. You see again that the molecular orbital diagram is not fundamentally different from the molecular orbital diagram of the CO. Okay, so we can again determine the symmetry types of our HOMOs, determining the reducible representation and the irreducible representation. And the result in this case would be that one of the ligand group orbitals has A1G symmetry, one has EU symmetry, and the last one has B1G symmetry. Okay, so now we can construct again our molecular orbital diagram for the sigma bonding. So here are our metal orbitals. So the 3D orbitals have EG, A1G, B1G, and B2G symmetry respectively. The 4s orbital has A1G symmetry, and the 4p orbitals have A2U and EU symmetry respectively. Okay, our ligand group orbitals have A1G, EU, and B1G symmetry respectively. Okay, now we can just again combine orbitals with symmetry, same symmetry type. So we can, for instance, start with A1G. So we see that one of our 3D orbitals is A1G symmetry, that's the PC square. The 4s is A1G. And also one of our ligand group orbitals is A1G. Okay, so that gives 3 molecular orbitals. The symmetry type A1G, we can again approximate. One will be bonding, having low energy. One will be anti-bonding, having higher energy. And the third one will be approximately non-bonding, having intermediate energy. Okay, so here they are. That's the 1A1. Here we have the 2A1G, and here's the 3A1G. Okay, so next we can, for instance, choose the B1Gs. So we see that one of our d orbitals has B1G symmetry. We have one ligand group orbital has the same symmetry, so that gives two molecular orbitals. Yeah, one is bonding and one is interbonding. Bonding one is the one B1G, the interbonding one is the two B1G. Okay, next we can, for instance, choose the EUs. So the 4p orbitals, or two of them, have EU symmetry. Two ligand group orbitals also have EU symmetry. Okay, what does that give? Well, overall, 4 molecular orbitals, but we have to consider degeneracy. That means that we have 2 degenerate orbitals which are bonding, which have low energy, and 2 molecular orbitals which are interbonding and which are also degenerate. Okay, so here are the bonding ones with lower energy. It's called 1 EU, and these two here have high energy. They are called 2 EU. Okay, so now what is left? Well, we have used all our ligand group orbitals, but we have not used all our metal orbitals. In particular, we have not used the EG orbitals, and we also have not used the B2G orbital. In addition to that, we also have not used the A2U4P orbital. So these metal orbitals, they remain non-bonding with respect to sigma bonding, and we have to write them accordingly into the molecular orbital diagram. You'll see that here. So now you see that our molecular orbital already looks relatively complex because we have so many different energy levels, but you see that you can nonetheless construct it systematically and understand it by just systematically analyzing it. Okay, finally, we still need to consider the electrons. So again, we say that we have a donor acceptor dative sigma bond here. So therefore, all of our electrons are coming from the ligand, the cyanoligand in this case. And we have 8 electrons to consider. So these 8 electrons would need to go into the 4 orbitals of lowest energy. And we see that all these orbitals are bonding. So again, we can nicely explain the 4 sigma bonds in our complex. And the square planar shape, we would also understand the stability of our complex. So all metal electrons would need to go into the B2G, EG, 2A1G, and B1G orbitals respectively. Okay? So if we had, for instance, 10 D electrons, this would fill all these orbitals here. So therefore, again, we can say that these orbitals here are our frontier orbitals, and that these orbitals here are our metal d orbitals that now split in the square planar ligand field. So these three here are exactly the dxy, the dxz, and the dyz because they're exactly non-bonding. But these two can also be approximated metal d orbitals. This one here, because made from the dz square, can be considered the dz square in the square planar ligand field. And this one here, because made from the dx square minus y square, can be considered to be the dx square minus y square in a square planar ligand. Okay, so this was the sigma bonding. We still need to consider the pi bonding as well, but we can do this in the next class because our time is over.